All right, so today starts our unit on basic probability and statistics and how those apply to business type scenarios. Probably in your business degree, you're going to have to take some sort of statistics-based class. And so this class is supposed to give you kind of a refresher / an intro to those topics. So we're going to look at some basic probability concepts today because I can't really discuss concepts of probability and statistics unless you have kind of a baseline. So that's kind of what today's lesson is going to be. So first of all, let's define what probability is. Probability is the chance that an event will occur. The formula for it is the number of desired outcomes over the total number of outcomes. So let's actually change that top word because events really mean something different. Let's see if I get my white out to work. All right, so when we discuss the probabilities of things, we're going to use some kind of common notation. So when you see a capital P and then something in a parentheses, okay, this means the probability of event A occurring. All right, so the first types of events that we're going to find the probabilities for are called simple events. Simple events is where we're looking for single outcome scenarios, as opposed to compound outcome scenarios, which we'll look at those as well, but just not right now. And then lastly, before we look at an example, a sample space for a probability experiment is basically a list of all possible outcomes. All right, so just to get the notation and stuff down, let's look at maybe a die with 13 sides. So the first question is, what is the sample space? So a sample space is just a listing of all the options. Okay. When you list values in math, you use curly braces and commas to separate your different values. So anytime you're listing out items in a long list or a set, you use the curly braces. So notice that I may not want to write all the way to 13, so you can do stuff like this as long as it's clear what the pattern is. So notice the ... implies that I need to keep counting until I reach what number in the end? 13. Okay, so it's important that I include that last number if I'm going to use this kind of shortcut notation. Okay, or you could just list them all out, but I mean, I'm trying to make it a little shorter here. So what's the probability of rolling a 7 on this weird 13-sided die? Okay. So how many options were there in my sample space? 13, right? So 13 goes on bottom. And then how many outcomes would qualify as what I'm looking for? Only one of them, right? So it's not, we don't count, the number isn't important, right? It's how many 7s are there, right? And there's only one 7. So we would say 1 out of 13. And then when you divide this on your calculator, remember that'll give you a decimal, and then how do you change that decimal to a percentage? Move the decimal place how many times? Twice, or you can just multiply by 100, okay? But you're going to need to know how to change these fractions into decimals and percents. So this would be 0.069 or about 7.69%. Notice I'm using the approximately equal to because it's not exact. 1 over 13 is actually a repeating decimal. Okay, so what if I start to get a little more difficult with what I'm asking you? So what about the probability of an even number? Okay, so again, how many choices total do I have? What should go on bottom? 13. Okay, and then I probably just need to count how many even numbers there are, right? It's not 1 out of 2 because this is an odd numbered sided dice, if that makes sense, okay? So we need to count how many even numbers there are, right? So 2, what else? 4, 6, 8, 10, 12. So how many was that? 6. So 6 out of 13. Okay, so let's figure out what that is on the calculator. I didn't do that one ahead of time. So if you have a calculator, go ahead and get it out in case I need you to punch something in for me. So that would be right around 0.4615 or 46.15%. And then what about this last one? So what about the probability of rolling less than 3? So again, how many choices do I have on this die? 13. Okay, so notice that should be my denominator all the way across. Okay, how many things are less than 3 on this die? 2 different things, right? The number 1 and the number 2, right? So that's 2 choices. And 2 divided by 13 is about 0.1538 or about 15.38%. Okay. Notice that if I changed just a little wording, what if I said 3 or less instead of less than 3? 3 or less would have included what additional number? 3, so there would have been 3 out of 13 choices, right? So make sure you pay attention to like the little nuances of the wording because that changes what it is sometimes. So before we look at another example, let's look at kind of the range of values we can expect. If an event cannot happen, then the probability of that event is what? What is the probability for something that will never, ever, ever happen? 0? Yes. Okay. If an event will definitely happen, then the probability of that occurring if we're in decimal form is 1. Okay, now what would the percentage form be for the number 1? Like if you move the decimal place twice, what would the number 1 mean in percentage form? 100%, right? So probabilities, all probabilities must be decimals between 0 and 1. Okay, if it's close to 0, what does that mean? Is it likely or not likely? No. Not likely, right? And if it's close to 1, what does that mean? Likely, okay? But the only things that are certain are if it's a probability of 0 and it's a probability of 1. Okay?
So do you want it in decimal or percentage?
It just kind of depends. Yeah, so if you want to, you could write under that, you could say something like, let's go ahead and write it, or percentages between 0 and 100%. So I'll specify what format I want it in. Basically, I want you to be able to change it freely from fraction to decimal to percentage form. I want you comfortable with all three, and then it shouldn't matter which one I ask you about. Okay, so let's look at another kind of common scenario in probability, because it allows us to ask really basic questions. So you might have seen a question like this on some sort of standardized test for you or your kids in the past. But the reason this type of problem is brought up a lot in probability basics is because you don't really have to have any background to be able to understand, items being drawn out of a bag of a total number of items. And a lot of times on most standardized tests, they'll use marbles, but honestly, the item is not important. Okay, the probability notation is what's important. So there are 3 marbles, or blue marbles, 5 yellow marbles, I spelled marbles wrong, and 2 red marbles in a bag. Okay, so what's the probability of drawing a blue marble? Okay, so same kind of stuff we've been doing already, right? So how many total marbles are there? 3, 5, and 2, so that's a total of how many? 10. And then how many blue are there? 3. Now this one, if I do it out of 10 or out of 100, I expect that you can change it to a decimal pretty easily, right? So what would the decimal be for 3/10? It'd be 0.3 or 30%. Notice I'm using a equals, right? Because this is not rounded, it's actually exact. When you have denominators that are nice, like 10, you can often tell what the exact one is. What about the probability of yellow? What would that be? 5 out of 10, right? When you can reduce the fraction I want you to, notice that reduces to 1/2. Okay, and of course, no surprise, but it's the decimal 0.5 and the percentage 50%. Okay, so we're going to look at maybe some other questions. So before we kind of do, I want to look at some deck of card basics before we look at the next few examples, because I'm not assuming that you have a lot of experience with a deck of cards, okay, but a lot of times you'll see probability questions referring to that because, the textbook kind of assumes that you've played a game of cards before in your life. But if you haven't, that's not the end of the world, so I'm going to give you the basics here. There's 52 cards in a deck. There's 2 colors. What are the 2 colors on most decks of cards? Black and red. There's 4 suits. The 4 suits are diamond, heart, club, and spade. There's 13 options. You can have ace, 2, 3, 4, all the way to 10. And then after 10, what comes if you've played cards before? Jack, queen, king. Notice if you wanted to list the ace after the king, you could. That wouldn't change the fact that there's 13 of them. It wouldn't matter the order that you would list them. And then something else that might come up is it might mention a face card. Okay, a face card is literally a card with a face on it. So which cards have people / faces on them? Not ace. Ace has just a big A. So just Jack, queen, king, yes. So a lot of people mistakenly think that the ace is a face card because it's a, quote, good card to get in most games, but that's not really the important. Literally, face cards means it has a person on it. Okay, so so we're going to look at some probabilities of maybe more than one thing occurring. So we've been looking at simple/single events, but we also can talk about the probability of more than one thing happening. Okay, so a compound event is more than one event occurring. And so this can look, this can look like different things, okay? And so let's look at the first set of compound events. So I want you to find the probability of rolling an even number that is more than 2 on a standard die. When I say standard die, what does that mean? How many sides does a standard die have? 6 as opposed to the janky 13-sided dice I asked you about before. Okay, so notice that I'm asking you about rolling an even number. That's the first requirement, right? But then I also want that number to be more than 2. So there's not really more than one event as much as there is more than one requirement, right? So the probability, let's go ahead and write the right notation. The probability of an even number that is more than 2. So I'm going to do the easy part for you. Okay, it'll definitely be over 6. And then we just, again, need to count and make sure we include both events, right, or both requirements, I should say. So how many even numbers are there that are more than 2 on a regular die? There's 4 and 6, right, which is how many options? 2. So we get 1/3 or 0.33, which is 33 1/3%, essentially. So let's look at another example that maybe uses cards this time. So I want you to find 2 probabilities. The probability of a black diamond in a deck of cards, and then maybe skip a space, the probability of a heart or diamond. Sorry about that, let me move it up. Okay, so both of these probabilities should be out of what? 52. Okay, what's the problem with the first question I asked you? Yeah, diamonds are red, right? So how many are there that are black diamonds then? 0. So what does that mean for us? That means it's not possible, right? So we get 0 or 0%. Okay, in other words, that's an impossible event, so it has a probability of 0. Okay, so what about hearts or diamonds? So we already said there's how many suits? 4, right? So if you split up the deck into 4 sections, there's 13 of each type, right? 13 of each suit. So if you have 2 different suits, then how many would that be? 26, okay? But what might have been a nicer way to think of that? I have 2 suits that I'm interested in, right? That are desired, quote, and how many suits do I have total? 4, right? So I could have also said 2 out of 4, but either one of those reduced to 1/2. So in the end, I want reduced answers when possible. Okay, if you have a repeating decimal like we did in Part A, just round it to 2 decimal places. That's usually the given. right, so we're going to look at a little bit more at compound events after a while, but I just want to get kind of a wide range of ideas across here. So let's list the sample space for a family with 2 children then I want you to use that to find the probability that both are girls. So notice this is a compound event because I'm asking you for the chances that kid number 1 is a girl, but also what else am I asking you for? That kid number 2 is also a girl, right? And so we'll talk about this maybe in another way, but let's do what the problem asked, which is let's list the sample space. Okay, so we're going to use B for boy, G for girl. Okay, so what are the different options of kind of birth order you can have? So I'll start you off. You can have boy, boy. You can have what? You can have 2 girls. You can have girl, boy, and you can have boy, girl. Okay, are there any other options? That's really it, right? That covers all of them, okay? So notice when we list a sample space, it tells us how many choices we have. So there are 4 choices. So now when I ask you for the probability that they are both girls, okay, it's going to be out of 4 choices, and you just need to look up at the list and tell me how many qualify as both girls. How many of the things that we listed qualify? Only one of them, right? So that would be 0.25 or 25%. Okay, so sometimes a sample space can be a really nice way for us to kind of figure compound events like this. Let's say I added a part B. So what if I asked you to find the probability of at least 1 girl? Okay, so I'm going to underline that. What does at least 1 mean? It means 1 would qualify, but what else would qualify? 2, right? In this case, that's the highest possibility, right? So the probability of at least 1 girl. So let's go through the choices. So I'm going to do the easy part. Again, it's over 4 because we already listed all the choices. So how many of those listed choices have at least 1 girl in them? 3 of them, right? The only one that doesn't is this boy-boy family, right? So this would be, of course, what? 0.75 or 75%. Okay. All right, so another terminology that you might see with this unit is the word complement. Notice it's not complement like I like your hair today. It's not spelled that way. It's got an E in it instead of an I. So complement spelled this way actually means the opposite. Or it means that the event does not occur. And this textbook, there's different notations for this. This textbook uses the following notation, but I've seen other textbooks use different things. So when you see A with a little kind of 1 up there, it doesn't mean to the first power. In probability, it means not A. So sometimes it's easier to talk about what something is not than it is to go directly for what it is. Okay, and I'll give you some examples, but so let's just get used to using the notation first. So in a standard deck of cards, in which you draw 1 card First of all, I want you to find the probability of diamond and then with a little 1 above it. Okay, so what does that read? What does that mean, or how does that read? What does this mean? It means not diamond, right? It basically means any other kind except for diamond. Okay, so we're going to talk about 2 ways we can get to this answer, okay? And I kind of need you to understand both going forward. So one would be to get it directly, right? So what are the other options other than diamond? We already kind of talked about it, right? Hearts, what else? Spades and clubs, right? So we're talking about 4 suits, right? So there are 3 out of 4 suits that are not diamond. Okay, or if you wanted to go with total number of cards, you would say 39 out of 52, because each suit has 13 cards. 3 times 13 is 39. Notice that these both, though, reduce to 75%. So I'm going to circle really all of these, because any of these are kind of are equivalent. But another way that is actually useful a lot of the times would be to talk about the probability of what you have and then just subtract it from 1. So what I mean by that is you could also say it's going to be 1 minus the probability that it is a diamond. Okay, notice this way involves having to count a lot less cards. Okay, so this would be 1 minus 13 out of 52, right? Which in the end would just be 39 out of 52, or 3/4. So notice they're the same. Okay, so sometimes it's easier to look at 1 minus the opposite occurring. All right, so let's say that the letter F represents face cards. And then let's say that I told you to find the probability of what? How do you say that? So what does this right here really mean? Yeah, so it means not face card. Okay, so for this one, I think we will go with the 1 minus thing. So in other words, we could find 1 minus the probability of face cards, because that's less cards to count, I mean. So let's think about that for a minute. Okay, so let's take 52 cards in a deck. So which cards are the face cards? The jacks, what else? The queens, the kings. How many of each of those 3 types are there? 4, right? So how many total cards are there then? 12. And notice if you subtract this, remember, so back to elementary school, fraction addition, right? What would you change 1 to so that you could subtract these fractions? You have to have a common what to add and subtract fractions? Common denominator. So 1 is the same as 52 out of 52. So then you just subtract them, right? So you end up getting 40 out of 52. But then you can reduce this by 4. 4 goes into both. So you end up getting 10/13ths, which, let's do that on the calculator. So that is 0.7692, or 76.92%. Notice that when I write out the decimals, I always use 4 decimal places. So that's so that when I do change it to a percentage, it still has how many? 2 decimal places. Okay, so I want your percentages to, in general, have 2 decimal places unless I say otherwise. Okay, so let's look at, there's a lot of terms I'm introducing to you today just because this is kind of an intro section. There won't be this many definitions every class time when we discuss these topics, but right at the first there's a lot. So there's two types of probability theories / thoughts. Theoretical probability is basically what should happen in theory. Okay, so an example is if I flip a coin 50 times, what should happen? It may not happen, but what should happen? So how many options are there when you flip a coin? 2, right? Heads or tails, right? So what should happen as far as how many heads you get? You should get exactly how many? 25. Okay? In a perfect scenario, that's what would happen, right? That's what, quote, should happen. But the reason I put that in quotes is that always going to be what happens? No, right? If you and I both flip a coin 50 times, neither one of us might get 25, and we probably wouldn't get the same number as each other, right? We'd probably have a different count of heads and tails. And so the second type of probability is called empirical or experimental. Those words are used interchangeably. So empirical or experimental probability is what actually happens based on results. In other words, it's not just the theory, right? It's what actually happens when you actually study it / record your results. So an example of that is maybe I flip a coin 50 times and I get 27 heads. Okay, so that's completely in the realm of possibility that I wouldn't get the perfect 25 and 25, right? But the law of large numbers says that the more often you perform an experiment, so the more frequent you perform an experiment, the closer your experimental probability should be to what you expected. Okay, so we are going to go to some business topics with this, just know that. Okay, so this might come into play. One example is if you were running a factory or something, or you worked at a manufacturing company, and you wanted to test to see, like let's say you made computers, okay, and you wanted to test to see like how many of the computers you're about to send out to the stores have some sort of error in the motherboard or something, okay. Would you probably test all the computers? Probably not so much, right? So you would pick a smaller group to test, right? But you wouldn't just test one. Why would you not just test one of the computers? Because we need to use the law of large numbers, right? You would need to test enough so that you would expect your experiment would more portray what the overall results were, right? So I'm not giving you a specific number, but you would need to test several of them, right? So maybe like 100 or something. So if you were making 10,000 computers, maybe you pick out 100 and you test those. Okay. It would be inefficient for you to just test 1 or 2 because that wouldn't give you very good results. Okay. Okay, and frankly, a lot of people don't understand the difference between these two probabilities. A lot of people. Okay. Anyone who goes and gambles and really thinks that they're going to win over the long haul doesn't understand the difference between these things, right? And I'm not knocking gambling because I've gambled before. And I probably will again because that's my grandpa's favorite pastime activity. He always makes me go to the casino with him. But anyway, so in theory, who's going to win if you play a gambling game? Like over the long run, who's going to win? You or the house? The house is going to win, right? But what we're betting on, literally, with our money, is that our experimental probability will be different than the theoretical probability, okay? And maybe it will once or twice, but what does the law of large numbers tell us about gambling in particular? If you do it enough, what's going to happen? What should happen is going to happen, which what quote should happen based on their rules for their games. They win, right? They set up every game so that they win, okay? Another real life example, if you're not a gambler, is have you ever heard people say, like, who are having children, I've had 3 boys, and so we're going to try again because this next one's bound to be a girl, okay? What's the flawed logic in their family planning? Like, does the 4th kid, not to be crude, but does the 4th sperm care what the previous 3 sperms were? No, like what's the chance of their 4th kid still being a girl or a boy, no matter if they've had 3 boys or not? It's still 50-50, right? Because those events don't have anything to do with each other, right? So what should happen is that 50-50 of every single kid is going to be a boy or a girl, okay? You don't get to say, oh, you know. So I've had people that are like still trying for 6 and 7 kids because they're still hoping that that last one is going to be a girl or a boy, right? And they may get a girl or a boy, but they still have the same chance they had on kid number 1 and kid number 2 and kid number 3 and so on and so forth, okay? So just some basic reasons that people don't understand basic probability if they think that that's going to make a difference. All right, so let's look at a problem where I just give you some numbers. So let's say the probability of some event A is 0.2, and the probability of some event B is 0.35. And then let's say I ask you to find the probability of C if the sample space is A, B, or C. Okay. So what does the sample space being A, B, or C mean? There's only 3 options, right? Now, right off the bat, these are not equally likely already, right? We already know that, right? Which one's more likely, A or B? B is more likely, right? Because it's got a higher percentage, okay? So because our only choices are A, B, and C, what do we know about the probability of A plus the probability of B plus the probability of C? What do we know about that for sure? Yeah, it'll equal, if we're doing percentages, it's 100, right? But we're going to say 1 since it's a decimal. But the reason is there are only those 3 options. So then we can figure out what this is, right? So this one was 20%, this one was 35%, and this one is, I'm not sure, right? So I should be able to solve, right, by adding these two. This would be 0.55. So what would the question mark be then? If you want to show some work, you could just subtract 0.55, right? So that means the probability of C is what? The rest of the 1, right? The rest of the 100%. Okay, so next time we're going to get into some more details about maybe more than one event occurring. But for now, I think this is kind of good enough to give you like a starter on what probability is. So just remember, if you're getting a negative probability, something's up, right? Because what do your probabilities have to be between? 0 and 1 if we're talking about decimals, right? 0 and 100% if we're talking about percentages. So if you get anything less than 0, if you get anything more than 1, then you've done something wrong because that's not possible. Okay? 0 means it can't happen. 1 means what? It is certain to happen. And then what's the general formula for probability before we talk about test 2? What's the general formula for probability? What goes on the bottom of the fraction? The total number of outcomes, right? And then what goes on the top? Like how many of what you want to happen, yes. Okay, so that's the gist of that formula.